I will be talking about 10 points in the cubic. But first, I thought we should talk a little bit about incidence and rigidity results in somewhat more generality. So let me start with one of the first theorems in incidence geometry, Pappus's theorem. Pappus's theorem you can find in his book, which he calls The Synagogue. The synagogue is like a collection of things. And the collection of things that he's talking about is a collection of kind of Greek geometric results that have been known for hundreds of years by the time that he's talking about them. And this is one of the incidence theorems in that book, and I really like it. I didn't actually learn it from that particular book. I learned it from this other book here that I've featured, Jürgen Richter-Gebert's book, Perspectives on Projective Geometry, which I like a lot. I wrote a short review of it for the American Math Monthly. And if you want the 5-page version of it, you can check that out. Here's Pappus's result itself. It's shown here. Let me start with 3 points, 1, 2, and 3 that are collinear, and 3 other points, 4, 5, and 6 that are collinear on a second line. And then let's join those points up. First with 3 lines, 3 new lines that connect the points. For instance, 1 to 6, and 2 to 4, and 3 to 5. And then 3 additional new lines that connect the points. So I've got 2 pairs of, ignoring the first blue lines that impose the coincidences, I've got 3 lines joining the 6 points and 3 other lines joining the 6 points. I don't know if you can see me, but I'm kind of moving my hands in this kind of grid-like pattern to suggest that those 2 sets of 3 lines should intersect each other in 9 points. And we already knew 6 of the points of intersection. So we get 3 new points, and I've called those 7, 8, and 9 here. And those 3 new points must be collinear, and that's Pappus's theorem. And in a sense, I think of this as a rigidity kind of result, that if your initial 6 points are constrained, then, and if you produce these new 3 points in this incidence fashion, then you have to have this extra red constraint. It's forced on you. In a sense, it's kind of looking at collinearities that constrain point locations instead of distance constraints that are constraining point locations. And so in that sense, I think this is a very appropriate topic for the rigidity semester. Okay, let's look at a few other classical incidence results. So one is due to Menelaus, and it's here on the left. It says that 3 points are collinear, 3 points A, B, and C are collinear when they strike the edges or extended edges of a triangle in a very special way. And the special way is recorded in terms of these products of quotients of oriented distances. So notice that I've got AC here, capital A going to lowercase c, and that's the distance from here to here. And then we divide by the distance along the rest of the segment from C to B. And then that's this first quotient. And then we multiply by capital B to A divided by A to C. And this A to C will be negative. So we're looking at oriented distances here. And then finally, we multiply by C to B times B to A. And this whole quotient, this whole product of quotients has to be -1 if these 3 points are going to be collinear. which is pretty cool. It's an interesting kind of incidence result that ties in distances. A kind of similar distance result is called Seva's theorem, and in some sense it's kind of analogous to Lemann's theorem in the sense of its history. In fact, Seva's theorem was discovered in the 11th century by a king of Saragossa, which is in present-day Spain, and then it was rediscovered by Seva and popularized by Seva, and in the 17th century, and it really today it kind of bears his name. But you can see the same product of distance ratios equaling 1 tells you that that these lines are coincident, that they intersect in a common point, which seems like special behavior as well. So these distance ratios are going to play a pretty key role for us in incidence results, and we'll have much more to say about this later. Okay, I'm interested in when 6 points lie on a conic. It's always the case that if you have 5 points in the plane, there's a conic through them. If the 5 points are in general position, there's a unique conic through them. But if the points are in kind of special position, then there's maybe more than one. Imagine, for instance, if 5 of the points were collinear, all 5 points were collinear. You could take any, you could take the line through those points and then any other line. And so you'd have a bunch of conics that go through them. But it's pretty special when 6 points lie on a conic. And Carnot found a nice way to express this condition that 6 points lie on a conic using these products of oriented distance ratios. And I'll just sketch it out for you again. Here we go from B to A1 and then divide by A1 to C. So that's the first term. And then we kind of keep going. We go from C to B1 divided by B1 to A, and then A to C1 divided by C1 to B. And then we go B to A2 this time, and then divided by the remaining portion, A2 to C, etc. And we keep going around, and eventually, if we get 1, then the 6 points lie on a conic. It's a nice result. Carnot himself was this like spectacularly interesting person. He was the Minister of Defense during the French Revolution, essentially. He was called the organizer of victory because he set up essentially all the supply chain for the French Revolutionary Army. And then eventually when he was ousted from the French Revolutionary group, leadership group, he actually managed to retire and keep his head, which is a pretty impressive thing. And he spent most of his time proving some pretty nice mathematical theorems after that. So kept his head lower. Anyway.
Hey, Will?
Okay. Yeah.
Just, I hadn't seen this one before. Does this also get, can you prove this by saying a certain determinant is 0? Like Siva and Menelaus?
Yes. Let me think about that. That's a good question. I mean, in a certain sense, yes, you can. There's a 6 by 6 determinant that tells you when, if its determinant is 0, then you can tell when 6 points lie in a conic. So in that sense, yes, but I don't know the actual direct link between that determinant expression and this distance expression. So in some sense, they're equivalent. So if that's what you're asking, yes. But if you're asking whether there's a direct proof that uses that phrasing, I don't know of it.
Okay, thanks.
Cool, yeah. And please interrupt with questions. Yeah, throughout. This would be great. All right, let's go back a couple centuries. Here's another result about 6 points lying on a conic. It's maybe better known than Carnot's result. It's Pascal's theorem. It was proved by Pascal when he was 16 years old. And, you know, at the time, I guess maybe it was common to produce a little poster and kind of put it up when you had a new theorem like this. It was a preprint server of the time, and he put posters around Paris advertising his new theorem with this nice incidence relation. It says that 6 points lie on a conic. You know, before we looked at Pappus's theorem, that was a degenerate conic, 2 lines, right? But now we're taking 6 points on a conic, on a regular conic. We're still doing the same kind of 3 lines covering all 6 points, meeting another 3 lines covering all 6 points. And that produces another 3 new points, and those 3 new points have to be collinear. So that's what these pictures are showing. And the nice thing about Pascal's theorem is that it's an equivalence. So in fact, if you, this result about 3 points being collinear characterizes when the 6 points lay on a conic, exactly. And I guess a converse direction was proved about 100 years later by Maclaurin and Breckenridge. And we kind of remember Maclaurin for Maclaurin series, I guess, today. But he had a role in this result as well. And I think this result is particularly nice because it kind of characterizes one incidence relation, 6 points lying on a conic, in terms of another incidence relation, 3 points being collinear. And my hope is to tell you about a generalization of this theorem today. Okay, Pascal's theorem was a bit controversial at the time, in fact. It's sometimes called the mystic hexagon theorem. And the reason is that if the 6 points are that you have are the vertices of a regular hexagon, then they lie in a circle. And so their points of intersection, these 3 new points, ought to be collinear. But the edges that you have to intersect, the lines that you have to intersect to produce these points, are these parallel lines. And so, you know, there's this question about where do the parallel lines meet? Like, where are these 3 collinear points? And, you know, the parallel lines, if they're viewed as meeting at infinity, right? And in P2, this makes a lot of sense. Then Pascal is saying that that all the points at infinity lie on a line, and that's somehow viewed as somewhat mystical, I guess, at the time. Not really thinking too much about projective space at that point. So so this is pretty cool, I think, and it took people a long time to kind of come to terms with all of the implications of these kinds of results, and eventually led to things like Bezout's theorem and you know, barycentric coordinates and all sorts of cool stuff having to do with projective geometry. I guess I have one more comment about Pascal's theorem before we kind of leave it, and that's that, let's just go back to it for a second. We get this red line, these 3 points on it, and we get it by, with this kind of combination of labels on the points. But if you relabel the points, then and reconnect them in the same kind of pattern, 1 going to 6 and 6 to 2, etc., then you get a new line, a different line. You still get 3 collinear points, and you just get a new line. In fact, there's 60 different ways to relabel the points, giving new lines. Some of the relabelings are trivial, and so they don't count, but there's 60 kind of non-trivial ones. And that gives 60 lines. And that configuration of 60 lines, it's called Pascal's hexagrammum mysticum. And it's been studied by almost every important geometer in the following years. It's kind of impressive how many people have their names on some aspect of Pascal's hexagrammum mysticum. I've got, in my notes, I've got Cayley, Steiner, Kirkman, Plucher, Salmon, John Conway. I mean, lots of people have looked at this. It's a pretty cool structure.
Will?
Yeah.
Is there any way to think about why it's 6, like 6 factorial divided by 60 is 12?
Yeah, that's a good
12?
question. So let's see. So 6 factorial is the number of ways of relabeling. But if I think it's something like a necklace situation. I think if I rotate all the points by 1, I don't create a new line. Maybe direction doesn't matter either. If I label 1, 2, 3, 4, 5, 6, and if I label in the opposite, kind of going around the other direction along the circle, I think maybe that accounts for it.
That would give 12, huh?
I think that's I somehow seem to recall that was the argument, but now that I'm saying it, it doesn't make that much sense to me. So but something along those lines probably is a correct reason.
Okay, thank you.
Yeah, cool. Yeah, no, good question. Yeah, wow. It's an awfully hard thing to draw, actually. And in fact, there were these 2 really interesting women in the 1920s, I believe, who got a PhD. They were sisters. They got twin sisters, in fact. They got, I think, a PhD at Yale, which is very unusual at the time for women mathematicians. And they their thesis was on drawing the actual 60 Pascal lines with all of the complicated things. It's quite impressive, actually. Anyway, okay. So, okay, Pascal's theorem then suggests that we really ought to work in projective space, and include points at infinity and things like that. But then you might become a little concerned, because like if we're working in projective space, then what's going on with all these distance constraints, right? Like distances are hard to work with in projective space because it's hard to kind of measure distances between points when you can scale the points. It's not impossible, but it's harder. That's one of the interesting things in Richter Gebert's book, but I'll just leave it at that. So instead of using distances directly, we're going to use cross ratios. So just as a reminder, a cross ratio of 4 collinear points, A, B, C, and D, is this product of oriented distances. So you take AC, that distance, times BD divided by AD over BC, like this. And if all the points are in, let's say, R2, then it's really easy to understand what this is. But you might get kind of concerned, like, well, what if I'm working in not R2? What if I'm working in P2? Or what if I'm working in, what if I'm even working over C2? And that's okay. What we can do is we can both orient the line, all lines at the same time, and we can kind of reinterpret these oriented distances in the following way. You take a point off the line, A, B, C, D, any point, doesn't really matter. And then this cross ratio also is equal to this ratio of determinants. And so I'm going to write my determinants as these brackets. And this, for instance, first one, OAC, refers to the 3 by 3 determinants that you get by taking the matrix of homogeneous coordinates, of O, A, and C. So the homogeneous coordinates of O are the first column, the homogeneous coordinates of A are the second column, and of C forms the third column. So it's a little exercise then to check that these two things agree when they both make sense, and that this extends things to to all these cases, and doesn't depend in particular on your choice of O. So it's kind of as long as it's off the line. And let me note, moreover, that these cross ratios are kind of projectively invariant. And so what does that mean? It means that if you were to multiply all your homogeneous coordinates by a fixed matrix, then this ratio wouldn't change. And that's actually pretty easy to see, because if you multiply each of the columns by this matrix and take its determinant, then you just get the determinant that you had before times the determinant of this multiplying matrix. So as long as the matrix that you're multiplying by is invertible, then it doesn't change this quotient, because you'll get the determinant squared on top and the determinant squared on bottom, and they'll cancel out. Change of coordinates, for instance, in projective space doesn't change the cross ratio. And also, as an example, projecting from one line to another line through a point also doesn't change the cross ratios of the points. So those are two important things that we'll use. And finally, the last thing about cross ratios that I want to mention for now is that if your point B happens to be the point at infinity, then you might get kind of worried, because some of these distances look like they're infinity over infinity. But actually, if you use this structure here, you can make sense of that, and these two terms cancel out, and so your cross ratio reduces to AC over AD, which is very nice, and we'll use this later. So
Hey,
this is, yeah.
One more question. You just said something like projecting from a line to another line through a point. Can you explain that a bit?
Yeah, sorry, I should probably have had a picture here. I'm kind of imagining that I've got one line here, and then I've got another line somewhere else, and I've got 4 points on this diagonal line, right? And now I've got some points over here, and I draw lines through this point. Let's call it, I don't know, O. Okay, draw lines through O, hitting this diagonal point on the diagonal line, and where it gets sent is this point on.
Will, what would we do? So if B is at infinity, we can use this other cross ratio.
So I'm sorry, say it again.
Sorry. So if B is at infinity, we use this other cross ratio AC over AD.
That's right.
What happens if, say, A or C or D is at infinity?
That's a good question. I think as well you get a product. You just get other terms that cancel. Like I think if C is infinity, this term and this term cancel, and you get BD over AD.
But I mean, I guess if 2 points are at infinity, then of the
2 points. So I'm only considering the case where the 4 points are distinct.
Okay.
But right, they're all collinear, so that's a different setup.
Okay.
I think then you get 0, 1 or infinity. I'm sorry. Yes, you get 0, 1 or infinity, and it kind of depends on which 2 points are set equal. That's right.
Okay. All right. Thanks.
Yeah, no problem. Alex, did I answer your question about projection?
Yeah, you did. I had missed that there were 4 points we were projecting, so that made sense. Yeah.
Okay, cool. Okay, so these brackets that we have here are going to play a central role in what we're doing. Okay, so I want to give the bracket equation for a conic. Okay, so let's go through this slowly. So the bracket equation 1, 2x. So I'm going to use this notation to say that I've got point 1. Okay, so it's just the name of a point, and second point, again, just the 2 stands just for the name of the point. And then I've got a kind of a third point, which is a variable point, right? It's got 3 coordinates, x, y, and z, homogeneous coordinates, but I don't exactly know what values they have yet. And if I take the determinant of this matrix, of course, I get a linear equation in the variables for x. And if I set that equal to 0, of course, I get a line, and that line happens to be the line through the points 1 and 2, because obviously if you put x equals 1 in here, you've got 2 columns being equal, and your determinant vanishes, right? So this is a nice, clever way of just saying what the equation of a line is, the line that goes through 1 and 2. And then suppose I've got, say, suppose I have 5 points, 1, 2, 3, 4, and 5, and I'd like to get the equation for the conic through all 5, right? Look at the conics through the first 4 points. There's what's called a pencil of conics. There's a whole family of conics that go through just 4 points. And I can give you 2 examples of conics that go through those 4 points. Here's one of them. It's the union of the line through 1 and 2 and the line through 3 and 4. Yeah? And so that union of 2 lines goes through the points 1, 2, 3, and 4. And similarly, the line through 1 and 3 and the line through 2 and 4 also is a second conic that goes through those points. And since there's a one-dimensional space of conics that goes through these 4 points, it means that every other conic that goes through those 4 points has to be have an equation of this form. Has to be a scalar times this equation plus a scalar times this factor equals 0. And now we happen to know that we want our conic to go through the point 5, right? So we could plug in x equals 5 everywhere, and we could see then a constraint on a and b. And you can see that if a is equal to 1, 3, 5, 2, 4, 5, if a is essentially exactly what you have over here in red, when you plug x equals 5 in, and if b is exactly what you have over here in blue, when you plug x equals 5 in, but with a negative sign, then it satisfies this equation, right? And so it tells us that the equation of the conic going through the 5 points, 1 through 5, is exactly this equation. And you can see that this equation is quadratic in the x's. It's got 2 x's in it. And so it gives us some kind of conic, and that conic happens to go through all of the points that we're interested in, 1 through 5. Okay, and so so that's the equation for the conic through 5 points.
Sorry for Will. What exactly is the bracket equation? Did we have a definition for that?
This little equation here?
Yes.
Yeah. Thanks for asking. This is the determinant of a 3 by 3 matrix, where the first column is the coordinates, homogeneous coordinates, so 3 coordinates, right, in P2, homogeneous coordinates of a point in P2 that we happen to know. And then the second column is the homogeneous coordinates of a second point that we happen to know. And then the third column is x, y, and z as the entries. And so we take that determinant and set it equal to 0. So these brackets are always the determinants of the 3 by 3 matrices with the columns listed here.
I mean, is this well defined with some of the other equations? Because it seems like it's either going to be non-zero or it can be a 0.
That's right. Thanks. Yeah, it's well defined, of course, up to scaling. So this bracket expression on its own, this is a very important point. Thank you for asking. This bracket expression on its own is only kind of makes sense up to scaling. And in fact, this equation here, you might say, well, I don't know. It looks like the left side can change if I scale, for instance, the 0.1. If I multiply it by lambda, right, and I'm allowed to do that, then it looks like this whole quantity is going to change. So how could it be equal to this quantity? But if you do that consistently, if you multiply the 0.1 by lambda, you'll get a lambda from here and a lambda from here, both factoring out of the determinant. And similarly over here, you'll get a lambda from 1 and a lambda from 1 over here. And so you'll get exactly the same factor coming out, and they'll cancel out. So this is well defined. So the points where this equation is satisfied, where this equality is satisfied, is well defined, even though each of these terms in it on their own don't define a well-defined function.
So you have to choose a homogeneous coordinate, a 3D coordinate, and you have to stick with it. That's the rule.
You could do it that way, or you could say you're allowed to scale, but you have, if you scale or change a point in one term of the equation, you have to do it consistently throughout the entire equation.
Okay. Yeah. Thank you.
Cool. Good question.
Bill, one other question.
Yeah.
Could you just go through one more time how you know that the conics through those 4 points are all and maybe I misunderstood something, are all defined by that equation that you have?
This one here?
Yeah.
Yeah. It's because, and this is not maybe totally obvious, that a conic through 4 points, should I say this? It defines a pencil. So it defines there's a P1 of conics that go through 4 points.
What's a pencil?
A pencil, that's a good question. So a pencil is a geometric object that behaves like P1, I would say. It's a parametrizing space for a collection of objects where the parametrizing space is exactly one-dimensional projective space. So think of it this way. If you take, if you write down a general conic, it's got 6 terms, right? The 3 x squared, y squared, z squared, and then all the kind of cross terms, xy, xz, yz, right? You've got 6 terms in it. And anytime you plug in a point and force that conic to go through that particular point, you're going to produce a linear equation on the coefficients of the conic. You're going to kind of constrain the conic in some way, right? And so you get a linear constraint. And if you put 4 linear constraints in, you should cut your space down from having 6 possible coordinates down to having essentially 2 possible coordinates, right? But even there, those 2 possible coordinates are like the 2 coordinates on P1. They, if you scale everything, if you multiply all the coefficients of a conic by the same number, then you don't change the curve, right? So that's the kind of hand-wavy explanation for why you get P1 of conics through 4 points.
Okay, so or just to dumb it down for me. So it seems like you just have a linear space of equations defining conics, and then this is you by fixing these 4 points, you've already put in 4 linear equations, and then now you just say here's a 2-dimensional space that satisfies these, so this is everything.
That's right.
Okay.
Exactly.
Great.
That's exactly right.
All right.
Yeah.
Thanks.
Will, can I also follow up? Could I say
Sure.
that a pencil of conics is the image of a map from P1 to the space of conics?
Yes. Yep. That's right. Yeah. That's right. Pencils of conics are a bit unusual. It's more common to think of a pencil of lines, and then that's the image of a map of P1 to a collection of lines. And typically we often think of the lines through a particular point, all the lines through a point in the plane, they form a pencil as well. So that's the situation you encounter more frequently.
Okay, thanks. I always just thought of one parameter, like groups in Lie groups, is sort of like pencils, maybe. Okay, anyway.
That's interesting. So here's our equation for the conic through 5 points. And if you want a 6th point to lie in that conic, well, then you just plug it x equals 6 in there, right? Your 6th point. And this is the equation that guarantees that the 6 points lie on a conic. And so this is kind of the bracket equation for a conic. Okay, so now I'm actually going to come back to some of these questions about well-definedness. So I said before that this is the equation that defines when 6 points lie on a conic, but I should observe, as we did before, that this is a well-defined condition, that if you scale each of the points, you don't affect this equality by scaling the points. And also you don't affect this equality by changing coordinates. If you were to multiply each of the points by a matrix, by the same matrix, then you get the 4th power of the determinant showing up here, right? Because each of these brackets is really a 3 by 3 determinant. And if you multiply each of the columns, again, by that matrix, then what you get is the determinant that you had originally times the determinant of the matrix. You can see then that the equality is going to be preserved. So there's some conditions on these bracket polynomials that need to be satisfied in order to be well-defined and projectively invariant. The well-defined condition is just that in each term here, each point, like 1, appears in the same number of brackets. So it appears in 2 brackets over here. It better appear in 2 brackets over here. Similarly for 2 and 3, etc. So that's going to guarantee well-definedness of bracket polynomials, kind of defining a nice condition for us. And we're going to call those properties that are determined by such conditions algebraic properties. So they're the properties that are determined by the vanishing of a polynomial. And you might think, well, those might be pretty special conditions, right? I mean, they're the ones that are algebraic. But it turns out that that every invariant algebraic property that you have can be written as a polynomial in these brackets. Yeah, so essentially, if you've got a property of your geometry that doesn't depend on the coordinates, doesn't depend on your choice of coordinates. For instance, 3 points lying on a line doesn't depend on your choice of basis, or 6 points lying on a conic doesn't, again, depend on your choice of basis for the ambient space. Then that property can be characterized by an equation kind of like this one, right? A bracket equation. And so that's pretty cool that these bracket equations, can describe all these invariant properties. But these bracket equations are not unique. I wrote down one bracket equation. There's other bracket equations that describe the same phenomena, that 6 points lie on a conic. And that's because the brackets are far from being independent quantities. So there's relations among the brackets. And so I want to explain how you get the relations among the brackets. Okay, so let's just do a little calculation. So I've got these 4 points here, and I've drawn 2 lines, and the intersection of those 2 lines I'm calling the point y. Okay, so y is the intersection of the line 1, 2, intersected with the line 3, 4. And then I claim that 1, 2, y is 0, this bracket. And that's just because the 3 points are collinear, right? So the bracket vanishes, the determinant vanishes, right? Also, 3, 4, y is 0, because those guys are collinear. Also, y is a linear combination of the points 1 and 2, because it's on this line. And similarly, y is a linear combination of the points 3 and 4. So I've written that here. Okay, but we can actually figure out what these coefficients a and b have to be. For instance, you can take this, this expression here for y and plug it in to this bracket 3, 4, y being 0. So when you plug it in, you get a times 1 here plus b times 2, right, for the y. And by multilinearity, when we express that bracket, you get a, this constant, times 1, 3, 4, plus b constant times 2, 3, 4. This is true, but it would have maybe been better if I had written this as 3, 4, 1 and 4, 2, 3, and 3, 4, 2, just to make it clearer that this was coming out of expressing this bracket. And then you get 0. And so that tells you that a should be 2, 3, 4, this bracket, and b should be negative 1, 3, 4, right? Or at least those two work. And so that y is expressed exactly like this, that it's this bracket 2, 3, 4 times the homogeneous coordinates of 1 minus, again, the bracket 1, 3, 4 times the homogeneous coordinates of 2. And again, you might be worried about scaling, but it turns out that when you scale, everything appropriately scales. And so this is well defined. So we can find the actual kind of coordinates of where y is in terms of 1 and 2. And similarly, if you plug this second equation into 1, 2, y being 0, you can get this expression for y. So we have 2 expressions for y. Y is a linear combination of 1 and 2, and it's a linear combination of points 3 and 4. Well, okay, so you could set them equal, right? And so you get this kind of quality of 2 bracket expressions. They're not bracket polynomials yet, because we've just got these points hanging around. But in order to make them polynomials, I could take that very complicated expression that I have here, and I could plug it in to as the first column of 3 by 3 determinant, whose other columns are points 4 and a new point 5. Okay? So what do you get? You get 2, 3, 4, and then 1, 4, 5, right? This 1 getting plugged in here, minus 1, 3, 4, right over here, 2, 4, 5. And then that's equal to 1, 2, 4, 3, 4, 5, and 1, 2, 3, 4, 4, 5. Well, we know what 4, 4, 5 is. That's a 0 determinant, right? 2 columns being the same. And then you can just rearrange the columns, rearrange things to get this bracket equation. And this bracket equation has to hold for any 5 points. So this is trinomial, 3 terms, trinomial quadratic, 2 brackets in every term, relation among the brackets in P2. So these brackets are not independent. They satisfy this interesting equation, which will be kind of important to us. Okay. All right. So now I want to focus on this equation. So I'm rewriting it here at the top of the screen. Okay. And it's a trinomial. And you may not have heard much about trinomials. We don't study trinomials much. We study binomials a lot, right? So you might be curious about, like, well, when does this trinomial reduce to a binomial? Well, if one of the terms is 0, then you could get a binomial. So for instance, what if this term was 0, 1, 3, 4? 1, 3, 4 was 0, then we would have these other two terms, their difference being 0, so they're equal terms, right? So whenever you have 3 points that are collinear, you get an equality of two bracket binomials like this. Two bracket, let's say, equality of two bracket monomials, really. And you can use this to cook up some nice proofs. I call this a binomial proof. For instance, if you try to prove Pascal's theorem, in Pascal's theorem, remember, we had a whole bunch of collinear points, right? We had lots of triples of points being collinear. And so they give us an equality of some bracket monomials. And then if you take all these brackets here and multiply them together, and take all these brackets here and multiply them together, you get something that's equal. It's got more terms than this, but a lot of the brackets cancel out. Like 741 is over here, and 741 is over here. So they cancel. A lot of the brackets cancel, and at least as long as none of the points that are not explicitly required to be collinear are collinear, then you're allowed to cancel these brackets because their determinants are not 0, and you get this equality. And this equality is exactly the equality that told us that 6 points lay on a conic. So this says that these linear incidence conditions imply that 6 points lie on a conic. I like these proofs a lot. They're not particularly easy to find by hand. If you're looking for such patterns where things cancel out exactly to produce such a thing. But I've written an integer programming problem that solves to find such proofs. And we'll see that later.
Will, so you're not adding up all these equalities to get the last equality?
No, you're multiplying them. You're multiplying them. So you get, on the left, you get like a huge bracket monomial, product of brackets. And on the right, you get a huge bracket monomial, a whole product, and then you cancel. Maybe you're looking at these minuses and pluses and thinking, oh, well, that means you're supposed to add them. But I've just put a minus sometimes in front of monomial when when there's a minus in the relation. So this product of brackets is equal to minus this product of brackets. That's why the minus is showing up there. Probably would have been better if I typeset it without the pluses.
No, that makes sense. Okay, thanks.
Okay, cool. Yeah, typesetting these things is actually harder than solving them. The integer programming problem. I still don't have a good LaTeX typesetter for this. But I like these proofs a lot. They're essentially black boxes in a sense, but you can at least verify that they're correct. Okay, so what's going on with these kinds of equations that we have, these trinomial equations among the brackets? There's more than one. There's many of these trinomial equations, and these quadratic equations actually generate all of the relations among the brackets. They're called Grassmann-Cayley relations. And so the second fundamental theorem of invariant theory, it says exactly this, that the relations among all the brackets are generated by these Grassmann-Cayley relations. And this is kind of curious. It tells us that we've got this thing that we could call the bracket ring. And the bracket ring is the ring whose variables are all, it's generated by these brackets. And the relations are all these Grassmann-Cayley relations, right? And so we're taking a kind of quotient ring. And what geometric object does that describe? Well, it actually describes, it's the coordinate ring for two geometric objects. One is the ring of invariance of 3 by 3 invertible matrices acting on 3 by D matrices. So there's D columns here, and the D columns are coordinates of D points. Okay, and that's one D points in the plane, and that's one kind of way to think about this ring, as it's telling you something about the invariance of D points in the plane. Another thing, way you can think about it is as taking the same 3 by D matrix, but considering the rows of the matrix this time. And then you get 3-dimensional subspaces of D-dimensional space, because the rows each have D coordinates, so you're in D-dimensional space. So there is another way to kind of view the same ring as telling you that it's the homogeneous coordinate ring of the space that parameterizes 3-dimensional subspaces of D space, which is the Grassmannian G3D. So it's kind of a nice interplay between invariant theory and kind of a different branch of algebraic geometry dealing with linear subspaces. And I mention this because it motivates us to think a little bit about linear subspaces, and that prompts us maybe to think about exterior algebras. So I'm going to shift a little bit to what's called the Grassmann-Cayley algebra. So the Grassmann-Cayley algebra is like an exterior algebra. And if that doesn't make that much sense to you, then don't worry too much about it. Because we won't be using it much, but I do want to say a few words about it. The elements in the Grassmann-Cayley algebra describe geometry in ways, I say, that are easier to interpret than bracket polynomials. And this, we'll see this in a couple examples. And the same elements in the exterior algebra, the Grassmann-Cayley algebra has the same elements as an exterior algebra. So the elements are the same, but they have two new operations, the join operation and the meet. So if you've got a bunch of vectors in a vector space, V, then you can take their join, and that's just taking their usual wedge product, their usual product in the exterior algebra. And if you took the join of D vectors, and if V had was D-dimensional, then the wedge product of D vectors is the same thing as the determinant of the D vectors. So that's why this makes sense for the bracket. But there's a second operation called the meet, which is a bit more complicated, and I'm not going to go into the details of it. But the join should, in some sense, be thought of as kind of giving the direct sum of, not the direct sum, but just the sum of two subspaces. So if these vectors define one-dimensional subspaces, then taking their join will define the space spanned by them. And the meet corresponds to taking the intersection of two subspaces. You've got a subspace here defined by m vectors and another subspace here defined by n vectors. You can take their meet, and what you get corresponds in some way that I'm not explaining to the intersection of these two vector spaces. So the Grassmann-Cayley algebra is a way to kind of try to do linear algebra in a sense, using the exterior algebra. And we can see that sometimes brackets themselves, well, always brackets themselves are expressed, can be expressed as joins, but sometimes very complicated bracket polynomials could be expressed maybe in terms of this meet and join operations. And when you can express a bracket polynomial as a Grassmann-Cayley expression, we call that factoring. the Grassmann-Cayley factorization. And it turns out that not every bracket polynomial admits a factorization, so that makes life a little bit more complicated. In the multilinear case, when each symbol appears once in each term, then Neil White designed a factorization algorithm. But in general, it's not possible to factor all brackets. And but Sternfels and Walter Whiteley proved that every bracket polynomial admits a Grassmann-Cayley factorization after you multiply by a bracket monomial. So, so what the heck does this mean? What I take it to mean is the following thing. Remember that that every bracket polynomial that kind of we're interested in expresses its vanishing, expresses some kind of invariant condition among a bunch of points, let's say. And what this says is that when you multiply by a bracket monomial, you can express that condition in terms of these meets and joins of linear spaces. And the point here is that when you're asking for a bracket monomial multiplying by a bracket monomial, what we're saying is that like the product here is going to be 0 in which situations? Well, in the situations that our original geometric condition held, the original polynomial, and also in the situation where like 3 points are collinear. So as long as a bunch of points are not collinear, as long as the points are in general linear position, then you can conclude that your bracket polynomial is being satisfied, right? So what we get is a way to express each of the bracket polynomials as something that says, yeah, you've got this expression in terms of meets and joins, and that's equivalent to your geometric condition, as long as some collections of 3 points are not collinear. So essentially, every invariant condition then can be expressed as a Grassmann-Cayley condition with non-incidence conditions as well.
So Will, when you when you have to multiply by a bracket monomial, that means you have to remove some bad
configuration of points. Yeah, that's right. You're not allowed to have points 1, 2, and 3 be collinear or something like that. Yeah, but as long as that bad configuration is kind of ignored, then you've got this factorization.
And you're always removing something that's a closed, Zariski closed set. So
that's right. That's right. It's always one of these 3 points can't be collinear. So, I mean, you might have a bunch of collections of 3 points that aren't allowed to be collinear, but that's there might be a lot of them, and the monomial might be quite high degree. And in fact, the original proof of this says the monomial being of some astronomical degree, but which makes it a little hard to implement in practice the proof. But that's the interpretation.
Could it be the case, like let's say you do have to multiply by a bracket monomial? Could it be the case that actually some configurations that you've now pulled away by multiplying by that bracket monomial, some of those configurations are still like the original relation actually holds there and it's okay?
Yeah, that's possibly true. So I believe in that situation that there might be a different bracket monomial that you could multiply by, where those 3 wouldn't be cut out, but and then you would get a factorization there. So you may be able to kind of, there's all these kind of configurations that you're kind of not allowed to be talking about. They're a closed subset of the configuration space. So it's kind of like almost everywhere these problems don't occur, right? But you might be able to kind of cover those with patches somehow that have a bunch of different factorizations, and one of these factorizations always holds, something like that. But I don't know any results of that nature. I'm just speculating.
Will?
Yeah.
So these are you're thinking about something like pure conditions, right?
Yes, and in fact, I'm about to talk about pure conditions in just a moment.
Oh, okay.
So,
and I guess then you'll also mention that usually we don't have a nice geometric description of these, nor a sort of an algorithmic test of these bad ones that are cut out.
Yeah, we'll come to that, and
Okay.
and we'll see what I say. Yeah. Here we are. Mira was asking about pure conditions, and here is a pure condition. So in this group, maybe I won't say so much about what a pure condition is right now, but imagine you've got a graph like K33 here, and imagine that it is realized in the plane. So we've got a configuration, and this is maybe a special configuration, and you're interested in whether there's a flex, okay, or whether this thing is not rigid, right? And so it turns out that there is a polynomial which you can evaluate that tells you when there's a flex, and that polynomial is called this pure condition. It's an odd name for it, but the pure condition is a bracket polynomial, and it turns out to be a bracket polynomial. And here is the pure condition for K33. So if you want to know if there's a flex for your particular K33, then you evaluate this bracket polynomial and check to see whether you get equality. And this bracket polynomial happens to factor. Okay, in fact, it factors in this way. So you take the line joining points A2 and B3, and you intersect it with the line joining points B2 and B3 to get a point. And you do the same thing here to get a point, same thing here to get a point. And then the join of these 3 points, meaning the line going through these 2 points, has to also go through this this third point. That's the interpretation. But you might think, 3 points lying on a line. I think I've seen that before, and you'd be right. This is exactly the condition for these 6 points to lie on a conic. So it turns out that K33 realized in the plane has a flex precisely when the 6 points that you're looking at lie on a conic. And you know, Mira was saying it's not so easy to first of all to factor these conditions into these expressions, and that's definitely true. Sometimes you have algorithms to do it, and sometimes those algorithms fail. There is a very nice algorithm by Susanna Pell, which often works to factor these things. So that's the most general algorithm that I know of. It's quite nice. But even then, the challenge of interpreting what the heck this means is a totally different, like, difficult challenge, right? I don't think any of us glancing at this for the first time would think, oh, that means that the 6 original points lie on a conic. So this can be pretty tricky. Mira, did you want to say more about this? Okay, we'll keep going. So you can factor pure conditions. Actually, I think I might skip the next couple slides and just, I'll mention one more example having to do with rigidity. which has to do with these robot arms. So here we've got a picture. It's taken from a paper by Neil White in the Handbook of Combinatorics. And on the next slide, I'll give you a reference for this, but it's got a robot arm in 3 dimensions, and it's got all these resolute joints. So these are joints that rotate a cylinder. You could think of them almost like the handle of a doorknob. It can rotate, but it can't translate. And here he's requiring a bunch of other conditions, that these 2 bars be parallel, and etc. But he's interested in paths that the arm can take, and motion planning for the arm if you want to get from one position to another. And what he observes is that that these motion planning algorithms run into problems when the arm is in what's called a critical configuration, when the joints, when they're extensors. So I should say you've got these points, 2 points in 3 space, and you could take their wedge product and get a point in the wedge product of 3 space, which is if you view 3 space as P3, then you get 2 points. You get a point in the second wedge product of C4, which is 6-dimensional. So so if 6 of these joints happen to be linearly dependent, that's exactly the situation when these robot motion planning algorithms kind of crash, they fail. So we might be interested in what are the configurations where that happens. And there's this thing called the super bracket, again, a name for some condition. And the super bracket is expression in terms of brackets. And that expression vanishes precisely when you're in one of these critical configurations, right? And it turns out that that super bracket can be factored. It's this very nice Grassmann-Cayley expression. And what this says is that when this Grassmann-Cayley expression is 0, then you're in a critical configuration. So that says that either the points C1, D2, and C2 have to all lie on a line, so they're not a plane, right? Either these guys lie on a line, or these guys lie on a line, or these guys, or the planes generated by these collections of 3 vectors, the 4 planes generated by them have to intersect in a non-empty intersection. And that kind of is a nice geometric kind of way to describe the critical configurations, at least in terms of things in 3-dimensional space itself, without having to rely on, second wedge powers of C4. So,
Will,
yeah.
the name super bracket, I just want to confirm it has nothing to do with like the coordinate ring of the super Grassmannian at all.
Oh, I have no knowledge of that, so I don't know. But
okay, there's no, yeah, okay. It's
my
just
guess is that it was just they came up with another name. To be honest, I'm not very keen on both super bracket and pure condition as names for things. I would rather call this thing like the critical configuration polynomial or something like that. That would make a lot more sense as a name.
Because there is a generalization of the Grassmannian, which is important, like in Manin's book on complex geometry and gauge field theory. But I'm assuming this is not that. So
I don't think so. But yeah. Here's a couple references to this first part of the talk. So in the Handbook of Computational Geometry, Neil White has a nice paper, and and Walter has a paper with Bernd on rigidity and scene analysis. So these are two good references. And then in the latest handbook of geometric constraint principles, Jessica and I have a paper that describes some of this work, and Jürgen, Richter Gebert, and Lee have a paper about coordinate-free theorem proving in incidence geometry, and they do this some of this binomial proof stuff. Okay, so so that concludes the first part of the talk, but I'm just trying to check my timing here, which of course I think we're beyond the first part of the talk. We started a little late, but all the same, I think I've taken more time than I'm allotted here. So I have a question then for Alex and Mira. How should we proceed? I think one thing to do is we could stop here. Another thing we could do is I could talk for like 10 minutes and just skim over what I think is a really interesting thing, or I could continue, say, next time and finish up. But that pushes the speakers back. I'm not sure we want to do that.
I mean, I guess I would love to hear you talk a second time. I don't know what Daniel or Tony or Mira would think.
Sorry, can I vote for you to continue next time, because my internet cut out and I've just got back in 5 minutes ago, so I missed about 45 minutes of your talk. Then I can watch the video and catch up next time.
That would be great. So
that's a personal choice, though. So if other people object, then feel free.
I think next time is, or yeah, just giving you another slot is fine. Just push everyone back a week. I mean, we'll check with the other speakers, but I think.
Okay. Yeah, I know we've done that in the past, so I kind of feel like if that's was, okay.
Yeah, I mean, like in designing this seminar, it was expected that we would have talks that would have to spill over into the next week. So that's totally expected.
Okay, thanks, guys. This is nice because I do have a whole second talk. I think in this first talk, I've tried to stress the connections between incidence and rigidity and some of the tools that we use for incidence, like bracket polynomials and distance relations and things of that nature, binomial proofs. I've tried to connect that up to some of the things that we see in rigidity, like the pure condition, the super bracket, and the Grassmann-Cayley factorizations. In next time's talk, then, what I'll try to do, just to advertise that, is I want to go back to Pascal's theorem. And Pascal's theorem, remember, said, when do 6 points lie in a conic? I'd like to prove a new result, which checks when 10 points lie in a cubic. And it will be very similar in spirit to this result. It will make some incidence-like constructions, and eventually we'll say, hey, if 3 points that we've constructed lie on a line, then the 10 points that you started with lay on a cubic. It's a kind of quite involved construction and proof, but it actually uses almost every bit of elementary geometry that I know. So which isn't all that much, but all the kind of most beautiful things in elementary geometry showed up again and again in the proof, and it's kind of a remarkable result. And so I'd like to talk about that next time. So this is a good place for us to stop.
So can I ask a question?
Of course, yeah.
You talked about these kinds of theorems as you wanted to see them as one type of rigidity, if one would like to see it like this. So then would you say that the result that you want to prove next time is also a rigidity result in the same spirit?
Yeah, I think so. I think, you know, the claim that the condition that that 10 points lie on a cubic somehow imposes extra constraints on your 10 points, that you should, and you should be able to see those extra constraints in some incidence structure. Now, it's not so easy to see that these 6 points lying on a conic is you know, a rigid constraint. But when you see that these 3 points have to lie on a line, it becomes kind of more obvious that the 6 points lying on a conic is in fact kind of imposing some kind of incidence constraint. Maybe not a linear incidence constraint on your original 6 points, but on these kind of derived points, then it does impose a constraint, and we'll kind of view it that way as well. So one thing that that I learned from Tony Jeremita many years ago was, he told me that polynomials are very rigid objects. And it took me a very long time to try to understand what that meant. And one of the ways that I think he might have meant that is that that there's a tremendous kind of structure in the points that satisfy polynomial equations. And in some sense, this is kind of pulling away the veil that blocks our view of what the structure is for cubics. So we'll see something more like an incidence relation like this for cubics. I don't know, Clara. Does that answer your question a little bit?
Well, it is. It's certainly a good advertisement for your next talk.
Okay. Thanks.
Yeah, so like with graph rigidity, you could think of it as the polynomials that require the edge length distances, squared distances to be equal, then have the unexpected further results that even the non-edge lengths have to be equal.
What do you mean by even the non-edge lengths? Well, there's some extra constraint on the
yeah,
non-edge
and so like the
lengths.
extra constraint of being on a line, or the extra constraint of being on a cubic, or the extra constraint of being on a conic.
That's right.
In graph rigidity, the extra constraints are the distance constraints between non-edges. You didn't explicitly require them to be fixed, but they end up having to be fixed just as a consequence of the other polynomials that you did enforce. Yeah.
Yes, that's right. That's right. That's right. That's the setup in rigidity theory in general, that that some of the fixed constraints imply the others, and the same kind of thing occurs here. Like for instance, in Pappus's theorem, some of the incidences imply this red incidence, and some of them imply this red constraint. It's not a distance constraint, but it's a constraint. It's a different kind of constraint, and it's kind of interesting in its own right. I would like to understand whether there's a way to kind of get a matroid description out of these incidence structures, but I haven't seen one yet. Yeah. Anyway, more things to talk about next week.
So you're talking to next week?
Yes, that seems to be the sense.
Great.
Go check with Lefteris, because
an apology.
Scheduled, but either newant week or the week after. Yeah.
Sure. Okay, that's cool. And I'll make my slides available too, if people want to review the material that we did talk about. There's a couple of things I didn't talk about and I won't talk about now, but You can read more about them, including a nice result by Jessica Sidman and Louis Theran and Audrey and Blumen Kai about characterizing when certain graphs have a monomial pure condition, which are situations where you can really easily interpret the pure condition vanishing.
And also Lefteris just told me that he's fine with you can go next week and he'll do the week after.
Sweet. Thanks, Lefty. Appreciate that.
I had another random question. Just
Sure.
So you mentioned that you have these like integer programming to just sort of generate theorems.
Yes.
I wonder, I mean, this is it's kind of silly, but the coordinate ring of the super Grassmannian, could you do the same thing with brackets coming from there?
I don't know.
This is something for me to think about. But the problem there is this coordinate ring is non-commutative. So I don't know if that would mess up.
Yeah, I guess if you could get a binomial relation, still, I think you might be able to do something. A lot of this really depends on the binomial relations. And the thing that I've noticed in using this solver is that I can often prove an incidence result directly, but when I can't, if you add extra information, you sometimes can give the solver enough extra information to kind of to work. And I'm thinking that, you know, in a lot of elementary geometry problems, you need to kind of identify that there's some clever point that isn't part of the original problem, but you're like, oh, consider the incenter of the circle or some special like incenter of some triangle. And then like once you draw that point, it's like, oh, everything becomes totally clear. And you're like, oh, now I see that I've got 4 points that are co-circular, and you work out some result that you want. But if you don't know to kind of start with that mystical special point that you're supposed to put, like see somehow that you're supposed to put down, it becomes like kind of an impossible problem. And that's kind of what happens in a lot of the integer programming formulations of these incidence results. If you can cleverly figure out what points you're supposed to be are supposed to be involved in the formulation, then the program finishes very quickly. And if you don't have the these clever points in there, then sometimes it doesn't work at all. So that's been my experience. It's been both kind of frustrating and very illuminating to me. Yeah.
So, Will, for that other question, the slide that you had of the Pappus theorem and all that, I don't know if you're planning to talk about that next week, but oh yeah, this one. So, I mean, essentially, you know, it's like geometry theorem proving. You could think of the theorem as a polynomial that's in the ideal generated by these other polynomials, right?
Mm-hmm.
So there's this, and you asked about the matroid. So there is an ideal, you know, a matroid that you can get, one or even possibly more matroids that you can get from the ideal theoretic, you know, from the fact that this polynomial is in the ideal generated by those. So has anyone actually looked at any one of those to see if it does anything useful in terms of proving geometry theorems?
I don't know, actually.
So there's this AMM paper that
Jessica and Lewis and
others wrote where they have
Yes, but just spent a lot of time with that paper, actually. So that's That's a really pretty paper. It just came out in the last couple of years about algebraic matroids in action. And you're right, we should think about it in that setting. Yeah, I haven't thought about that, but that's worth thinking about.
Or even from a variety like what Dan has done, you know, algebraic matroid starting from like from a vanishing ideal perspective.
Huh.
So I don't know. I mean, my question would be whether, I mean, this particular question that you posed as to how to capture geometry theorems without going through the whole ideal membership business, maybe a simpler way to deal with the matroid after cutting out some quote unquote bad or non-generic cases. That's been occupying people for, I mean, I think I've heard so many people say something like to that effect for many, many years, but looks like there's some obstruction that stops us from doing it. And I mean, I haven't really figured out what that is.
Yeah, that's right. I don't know. I do think that it's possible that the incidence structures may turn out to be much larger matroids, if they are matroids at all, than the rigidity matroids are. Yeah, at one point I wanted to know about whether there was a kind of forbidden minor characterization of rank. So, you know, if you've got 8 lines like this, forget about the red line, then each collinearity imposes some kind of constraint on your configuration space of points, right? Obviously 2 and 7, you can't put 6 wherever you want. It has to be on this line. Okay. But then when you try to impose this last constraint, there's no flexibility for where 7 is. It has to be here. It can't be in some other spots. And so this red line doesn't actually impose an independent constraint. It's dependent on the rest, right? Yeah. And so I would like to know what are the configurations of lines that give you dependencies like this. This is one configuration, but there's many others that give you dependencies. My hope was that there was some kind of finite set that would somehow describe kind of what the obstructions were to having linear independence of the constraints. But I asked Jun He about this, and I trust his intuition a lot more than I trust mine. And his response was, "There's no possible way that such a thing exists." So,
I sort of tend to agree that my guess is that if you cut out the sort of quote unquote bad cases, then you end up cutting out a lot of interesting cases. Almost all the interesting cases. So you just end up saying things about stuff you're not really interested in. So, I mean, all of geometry theorem proving is essentially finding dependent constraints from a set of independent constraints. So another unrelated question I had is, so the people who do like 5 points determine a conic or something like that, everybody knows, quote unquote, knows that. But then there are different groups of people who study them, like the people who do interpolation and stuff, you know, using parametric curves. So they have these conditions on, if I want the 6th point also on the conic, where should it be? And a different way of understanding it besides saying, oh, it has to satisfy these other conditions using brackets. I don't know if you've ever, if the two communities even talk to each other.
No. Where would I look for such a?
Okay, I'm putting a link on the chat that I found just searching randomly for this kind of thing, but.
Okay, excellent. Yeah, this would be interesting. Okay, I'll have a look at this and because yeah, I think actually it gets you thinking about some of these things gets you into very dangerous waters. When you think about, well, it's complicated to talk about a cubic equation and whether 10 points lie in a cubic, but it's easier to talk about like when 3 points are collinear. And you can say that to yourself, and that on some level that's probably true, but on another level, it's kind of like, why is it easier to say when 3 points lie in a line? Well, you just draw the line through 2 of the points and it goes through the third.
Yeah.
Well, drawing a line is not an easy operation. Turns out that we like to think of it as being trivial, but actually, finding mechanisms that draw lines and things like that was a whole complicated process.
Yeah.
So so there's all sorts of questions along these lines when you try to actually get into mechanism design, or you try to actually get into like machines that are going to actually check these things for you, whether this is so easy or not.
Mm.
And the question about whether you're interpolating points often comes down to questions about numerical stability and things like that in your algorithms. Yeah. And what I'm hoping, although I have nothing more than a hope, is that some of these Grassmann-Cayley kind of expressions will turn out to be more numerically stable than checking a kind of big determinant equation. But they may be exactly the same.